I'm going to be talking about the gravitational wave picture for seeing neutron stars instead of seeing with neutron stars. And so, here, okay. So what that means is, so the key thing, and by that we're going to bring this back to some of the, okay, we're going to bring this back to something that Andrew talked about at the beginning of the morning, which is that since the gravitational wave signal is sensitive to the mass quadrupole moment, what you're really probing when you look at a gravitational wave from a neutron star is the bulk movement of the densest matter. So if you look at a gravitational wave signal from a neutron star, you are no longer sensitive to any of the magnetosphere or the outer crust or any of the low-density, dynamic, interesting stuff that most electromagnetic astronomers spend their time worrying about. But instead, what you're probing is the core behavior of the neutron star. So well, most of the time they're far enough apart that that's not important. This gives you an opportunity to look deep inside the neutron star with gravitational waves. Okay, so binary neutron stars are one of the most frequently expected signals for advanced LIGO. In particular, with design sensitivities, we expect to see between 0.4 and 400 binary neutron star coalescences a year of observing time, with the mean around 40, but this is a part where not seeing anything is going to start to, at the very least, cut into the parameter space of population synthesis models. Advanced LIGO is being built. This is a quadruple suspension system that's holding the test mass that's right here. The bigger masses behind them are just reaction masses for control systems. There's currently also a site in the Kamioka facility being excavated for a Japanese gravitational wave detector, a third installation in India being proposed, and the European GEO is running currently in astrowatch mode just in case Betelgeuse goes supernova in the next year or two. But of course, when the advanced detectors go on, we're not going to jump exactly to the design sensitivity where we expect to see 40 signals a year. If you want to see some of the proposed observing scenarios, there's a reference that will be in the PDF that you can go to. But when an advanced LIGO turns on, its horizon distance, the farthest thing that it's going to see, is going to be less than half of its eventual horizon distance. So it's going to start, and those rates are going to be a few percent of their final expected rates. So we're not going to turn it on and immediately expect to see things. There's going to be a timeline of sensitivity improvements, increasing range for binary neutron stars, and a similar progression for the other detectors that are being commissioned right now. So there's a caveat when someone talks about an astrophysical sensitivity or an astrophysical survey, they're usually going to be talking about the design sensitivity curve, which is expected for advanced LIGO to be reached around 2019. Okay. So I had, given the PDF restriction, I had planned to flip through a sort of movie of a simulation later, but I'm sort of regretting that decision right now because that's going to be about 5 minutes of my 15 or 12-minute talk here. So when we look at a gravitational waveform, the analogy to consider is that you're hearing something. This means that we have actually a very precise knowledge of when it happened, not a very precise knowledge of where it came from. Most of our knowledge of the sky position actually comes from timing from different locations and triangulating to find out where the signal was. You get some information about the mass, distance, and configuration from the loudness of the signal. But the interesting thing is that we have a signature of the mass of the system that's creating a coalescence signal in the phase evolution of the wave itself. So this is This is something that is independent of our knowledge of the distance to the system or anything like that. We can just look at the dynamics, and from it we measure some combination of the masses. And in the same phase evolution, if you go to higher and higher, more smaller and more difficult to pick out terms, you get information about the spins of these objects. And in the case of neutron stars, we may be able to also consider something about how deformable they are. And deformability is interesting because Andrew mentioned it as one of the macro scale parameters of a neutron star that we expect to be able to use to constrain the equation of state. This particular picture is an example of the kind of sky localization you can expect. We're measuring this in degrees at the best. And you can see that there's some areas of the sky that are very poorly localized. The sensitivity of the detectors isn't a uniform across the sky. It's sort of a peanut blob above and below them. So we detect a signal, and then when we try and figure out what it was, this is an example output of a parameter estimation pipeline on a test signal. You can see sort of details of the current status of what LIGO scientists are actually doing to estimate the parameters of these systems. But here's an example where we have the two masses, the two component masses in some distribution. But the thing I want to point out here is that really you're measuring in this two-dimensional space, you're measuring one dimension much more tightly than you're measuring another dimension. So we're not really measuring masses. We're measuring this combination of masses called the chirp mass, and then another parameter that is something like the mass ratio. So it's not always going to be the right idea to take the parameters that you get from the gravitational wave and relate them directly to the parameters of individual sources. An example of this is in the paper that I reference on the next slide, where they also consider correlations that come in with masses as well as spins, and what that implies for, say, trying to distinguish between a neutron star and a black hole in a given observation of a compact binary. One of the things you can find is that the spin of one of the objects in the system can mimic the phase evolution contribution of the mass ratio. So again, you have this sort of characteristic banana shape in the mass-mass plane. But here, if you assume no spin, you get a smaller range of possible values. But if you allow spin to be unrestricted, you can get something that, for particularly not very loud signals, is going to give you a really wide range in the individual mass that you can constrain for an individual system. So you measure system properties as a whole much more easily than you do sort of individual properties. If you restrict it to the kinds of spins that you actually see in binary neutron stars in our galaxy, you're doing better than this worst case scenario. But this is something that we need to be careful of when we try and interpret results. Okay, so the first answer to what advanced LIGO is going to see is this expected 40 systems a year, most of which will have SNRs about this, which will give us some sort of mass constraint analogous to the one that is shown in this plot. So the other thing that I wanted to talk about was how this translates into understanding about the properties of the core of the neutron star. And to think about this, if you have an orbiting system, each of the masses is in free fall, the next to the leading order contribution of their gravitational interactions after the orbit is going to be the tidal deformation. So this is the same thing that you have in the Newtonian description of orbiting stuff. So you have your two things orbiting each other, and they have a tide that's induced on each star. We can parameterize this in the limiting linear case as just this parameter that characterizes how much a star is deformed relative to the strength of the external tidal field. This is the parameter that's appropriate for describing the modifications to the gravitational potential in the space-time around the deformed star. wow, that went a lot faster than I hoped. So let me just skip this and try and show you an example of where this comes in. So here are two equations of state. At the top, this is an equation of state that has large radius stars, at the bottom, compact stars. And as they start out, they're orbiting each other, and you have the gravitational waveform that is emitted by the system. The larger mass stars end up orbiting and colliding sooner than the other stars, partly because they lose energy at a faster rate. Part of the energy is going into the deformation, and also because they're larger, so they hit each other earlier. But even as they touch each other, the waveform is going to look sort of like a regular in-spiral waveform, and until a little bit later, as they're merging, it still looks like an in-spiral. It's still a quadrupole that is similar to an orbiting system. It's just that they're in contact now. And it's not till a little ways after that you have the two stars have merged, the gravitational wave amplitude goes down. This is a little later than that, and you have some stuff happening afterwards that we probably won't be able to see, so I won't talk about it. I'll also skip the black hole neutron stars. The interesting thing is turns out that we seem to be able to describe the merger by the same parameter that characterized the early in-spiral, which is a little weird because when they're merging, you can see that this sort of linear tidal deformation should no longer really be expected to apply to the characteristics of the system, because as they're in-spiraling, the in-spiral waveform continues up to well after the two stars are in contact. Whoa, where are we here? Okay. So this means that we can use this parameter as the characteristic that describes the system, and if you work through the amplitude of the differences between the waveforms that you get out and compare them to the expected sensitivity, find that only using the numerical simulation data, you can distinguish between interesting radii, effectively, at interesting distances where we expect to see either maybe 1% or 10% of the signals in advanced LIGO. If we have a hybrid construction where we take an analytic approximation for the in-spiral and match it onto the numerical waveform, we get distinguishability for most of the signals that advanced LIGO would see, marginally. But there's systematic errors that come in that are larger for hybrid waveforms. And this becomes something that's trickier to actually use with confidence. But if we do have a waveform model, this is a full Bayesian analysis of an injected signal population using an approximate waveform model. And you expect to be able to distinguish between equations of state with a reasonable number of events. We think there's this much information available in the waveforms, but the limitation of accurately modeling the phase evolution to be able to extract this information is the limiting factor. The interesting thing to point out is this systematic error would go away if we had infinite computer resources. So this isn't an uncertainty in modeling in the sense that we're not sure what to model. This is an uncertainty in that we're incapable of solving the general relativistic and hydrodynamics equations with perfect accuracy for long periods of time. And I'll just stop there.
In your finite-sized neutron star mergers, did you include the effects of viscosity and neutrino emission? And if not, what changes would they make?
Right. So the equation of state stuff I talked about is all cold, perfect fluid equations of state. For the in-spiral, we expect that to be a good approximation. The viscosity timescales are much longer. Wait, what's this? What am I trying to say here? So if you estimate the impact of viscosity, it should not change the hydrodynamics for this kind of system.
So in regards to your last slide with the Bayesian inference, when you say Bayesian immediately, I think of prior distributions. And so I'm curious if you, in this calculation, had an opportunity to vary your prior distributions, and what kind of changes did you get?
Right. So this I didn't contribute to this work. Okay. So this is I was trying to. Sorry, I should have emphasized more which stuff was other people that I was citing, but you can go follow the references. So I don't recall how they changed their prior distribution. You can see from where they start out, though, that it's not very. It starts out very all over the place. So I think that's some indication of prior independence. But you'd have to look at the paper for details. I don't remember.
Oh,
right
yes.
now.
Okay. We'll look at it. Thanks.
So I don't know if you can easily go back to slide 4, but you kind of concentrated on
Might be faster now.
on black hole neutron stars through most of your talk. So
Sorry, I was talking about binary neutron stars for most of the talk. There was one slide about black hole neutron stars.
We sped it up.
Yeah,
We
that
sped it up
means-
now.
okay.
If you want to go back.
but the projection was out to 215 megaparsecs when it's optimized. Is it farther for black hole?
Yeah, so the larger the mass, the farther the waveform can be seen.
Yeah.
So that's actually one of the issues with using so there's some cool stuff cited at the slide that you mentioned, or one of the slides about black hole neutron stars, where there's similar prospects. If you have a close enough black hole neutron star, you can measure the effects. But the rates for black hole neutron stars are about 3% the binary neutron star rate, so you don't expect as many of them close enough to be able to distinguish this kind of higher order effect.
And we, even though we don't understand rates very well, we think that it's 3%. We understand that it's 3% pretty well.
Well, they
Whatever
both
the-
have these orders of magnitude uncertainties, so I don't know how correlated the uncertainties are between the two types of system.
All right, thanks.